Laplace's expansion is a different way to compute the determinant of a matrix. It is in some cases more efficient to compute the determinant for a matrix. It is not always more efficient. In general, the row reduction method, where we just do row swaps and adding scalar multiples of one row to another row, and reducing to echelon form, that's a computationally efficient way to find determinants, so that's something that you would have a computer do. But in certain examples, Laplace's expansion can be really useful and efficient. And it also is useful for some other things. So anyway, let me show you how to do this just by example. So here's a matrix that I want to compute the determinant of 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So Laplace's expansion basically says this. It says that you could expand on a row or a column, and so I am going to do Laplace's expansion on the first row to show you what's going on. And so what I do is I do the following. So I'm going to do the first entry, which is 1, times the determinant of, and then I'm going to remove row 1 and column 1 from this matrix, and then I'm going to take the matrix, the submatrix that is left over from that, and I'm going to take the determinant of that. So 5, 6, 8, 9. We're going to take that determinant. Okay, so that's step 1. And the next thing that I do is I go to column 2, and then I'm going to go to column 3. So for column 2, you would have 2 times, and I remove again row 1 and column 2, row 1 and column 2, and the entries that are left to make up another submatrix, which would have the entries 4, 6, 7, and 9, and then I take that determinant, 4, 6, 7, and 9, and then I'm going to do the same thing for column 3. So I'll remove row 1 and column 3, and I'm left with 4, 5, 7, 8 as a matrix, and I multiply that by the entry 3. So times the determinant of 4, 5, 7, 8. Okay, so I have these 3 terms right here, and what I do is I'm going to take an alternating sum of these. So I do positive 1 times this thing, subtract the second one, and then add the third one, and then if this were like a 5 by 5, then I would subtract the fourth one and add the fifth one. Hopefully you get the picture. So yeah, that's how you, that's basically the idea, is that you can expand along a row or column to write this determinant, this big determinant, as a linear combination of determinants of smaller matrices. So you have a bigger matrix, and then you write it in terms of determinants of the smaller one. And since these are all 2 by 2 matrices, then we have a nice formula for what the determinant of all of these guys should be. And so we can finish this example out. So I have 1 times this first determinant should be 5 times 9 minus 6 times 8, minus 2 times, and that'll be 4 times 9 is 36, minus 7 times 6 is 42, plus 3 times 32 minus 35. And this is equal to, so this one would be 45 minus 48. So then this term right here would be negative 3. this term right here is -6, and I'm multiplying that by -2, so I'm going to add 12. And then this last term right here would be -3 times 3, so I have -9 right here. And so this sum is equal to 0, and so I can say that my determinant is equal to 0. Okay, cool. So right now I am not explaining at all why this is true, but I will tell you that that where this comes from is essentially using permutation matrices. It uses the permutation expansion of the determinant, and it sort of rearranges things and puts it into a nice compact way that it basically, you can use the permutation expansion to simplify the determinant to give you something like this. So I don't want to say too much more about that. What I really want you to get out of this first video is how do you compute these things. Okay. Right, so that's our first one. So definition, for any matrix, for any square matrix T, it's an n by n matrix, the ij minor of T is obtained by deleting row I and column j of that matrix. And so in our previous example, what we were doing was we were taking the determinant of a bunch of minors from that first matrix. We were deleting, in our case, we were deleting row 1 and columns 1, 2, and 3 of our matrix, and then we were taking a determinant. And specifically, we were also taking an alternating sum of those determinants being multiplied by the corresponding entry in the matrix. And, and so the next part of this definition, the ij cofactor, which we denote by capital T sub I comma j, this is basically what we were using in the previous example, where we take that ij minor of T and we take the determinant of that minor. And also this -1 to the I plus j, this is symbolizing the that alternating sum that we had. So let me maybe relate this to that first example. So -1, so we were expanding along row 1, right? So this, let me get rid of that for a second. So we were expanding along row 1, and so like the 1, 1 cofactor of this matrix was -1 to the 1 plus 1 times the determinant of the 1, 1 minor, which was 5, 6, 8, 9. And this -1 squared is equal to +1. And so that's where the alternating sum started. And then for the 1, 2 minor, this would have been a, let me do like a different color. This would have been -1 to the 1 plus 2, and that would be equal to -1. And then if I did -1 to the 1 plus 3, then it would have been positive again, and so on and so forth. So let's do a different example with this matrix. So so here I have the row 2 and column 3 of this matrix, and so the 2, 3 minor of T is obtained by deleting the highlighted rows, row 2 and column 3, and you obtain the matrix 1, 2, 7, 8, and the 2, 3 cofactor is negative 1 to the 2 plus 3 times the determinant of, well, let me use square brackets, times the determinant of 1, 2, 7, 8, the 2, 3 minor. And so this is negative 1, 2, 7, 8. Okay. Cool. Something to note, and that'll hopefully make your lives a lot easier. So the sign of negative 1 to the I plus j, which basically this is just saying what is the thing that you have to multiply your determinant by in your cofactor. This follows the same pattern that is shown in this matrix right here. So the 1, 1 cofactor would be multiplied by negative 1 to the 1 plus 1, which is 2, so it should be positive. And then, like we said before, the 1, 2 cofactor should be multiplied by negative 1, the 1, 3 should be multiplied by positive 1, and then 1, 4 is negative, 1, 5 is positive, so on and so forth. And then if you were to start in row 2, then that would alternate because you would be like adding 1 to all of those things. So negative 1 to the 2 plus 1 is negative, so on and so forth. So to know what this is, you don't always have to actually calculate negative 1 to the I plus j. You can just kind of use this pattern. So for 3 by 3 matrices, you have this pattern, and for 4 by 4 matrices, you have this pattern, and so on and so forth. In particular, it's useful to realize that the diagonal is always going to be positive, and but that's not necessarily true for the opposite diagonal. So for the 3 by 3 case, the opposite diagonal is positive, but for the 4 by 4 case, the opposite diagonal is negative. But for the actual diagonal of the matrix, where I and j are equal, then this sign is always going to be positive. Okay. So theorem, Laplace expansion. This just formalizes the example that we just talked about. For an n by n matrix, T, the entries of T are going to be given by T sub ij. We could find the determinant of T by expanding on any row I or any column j. So there are two options. We could expand on a row, row I, or we could expand on a column, column j. If we want to expand on row I, then we could say that the determinant of T is equal to this. So I take my entries in my matrix, I take the entries in that row, so the entries in row I of T would be Ti1, Ti2, Ti3, up through Tin. This is an n by n matrix. And all of these are multiplying by the corresponding cofactor for the matrix T. So you multiply the entry times the determinant of the corresponding minor of the matrix, and then also multiply by the corresponding sign as according to, let me scroll up for a sec, the pattern in that matrix. Okay. And then similarly, you could expand along a column and get the same sort of thing. So T1j, T2j, Tnj, those are the entries of T. And then capital T, 1j, capital T, 2j, these are all of the cofactors. So the determinant of the minor times the corresponding sign times the correct sign. Okay, so let's go back to our example and let's expand on a row and show you how that works. So I also want to expand on not the first column so that you can see what's going on a little bit better. All right, so we're expanding along column 2. So I'm going to take the first entry of that column times the corresponding minor. So I remove, so for the entry, for the 1, 2 entry, I remove row 1 and column 2, and I'm left with the matrix 4, 6, 7, 9. Let me move this over a little bit. Right? And then do I multiply by positive or negative 1? Well, I could go up to my pattern, and so the 2, 1 entry is always going to be negative, right? No matter what. So this should be negative. And then the next one, I will be adding, let me get rid of that. It's not working. Let me back out a second. Okay. Delete that, wrong one. Delete that. Expand. Now I take the 2, 2 entry, 5 times the remaining determinant of the remaining submatrix, and then do the same thing for the entry 3, 2. And this one is subtracting, right? My sum is going to be alternating. And then multiply by 1, 3, 4, 6. Okay, so hopefully this example makes sense. And then let me just finish it out just for completion's sake. So here I have 36 minus 42 plus 5 times 9 minus 3 times 7 is 21 minus 8 times 6 minus 12. This is equal to positive 12 minus, what's that? 12, 60? Is that 60? Maybe it's 60. And then minus 8 times negative 6, that would be plus 48. And 12 plus 48 is 60, so this whole thing is 0. Okay, and so this is the exact same determinant that I got from my previous example, so I trust this answer. So that's how you expand along that column. Okay, cool. I want you to try this next example on your own. Once I explain the problem, pause the video and get out your pen and paper and try this one out for yourself, just to see if you understand what's going on here. So what's special about this example, other than the fact that it's a bigger matrix, is that if a row or column has a lot of zeros, then that should tell you that it's a good candidate to expand along. So I might just hand you this matrix and ask you, what is the determinant of this matrix? And maybe naively you say, oh, all right, well, let me just do cofactor expansion on the first row. Then you would have 1 times a submatrix, 1 times a cofactor minus 2 times a cofactor plus 4 times a cofactor minus 2 times a cofactor. And those cofactors are all going to be involve determinants of 3 by 3 matrices, 3 by 3 submatrices. And so those you would have to do cofactor expansion on those to figure out those determinants as well. And that's 4 more things that you have to take determinants of, and that's a lot of things. So but if you have a bunch of zeros in there, then a bunch of your terms in your cofactor expansion are just going to be 0, and so you won't even have to bother calculating those determinants. So anyway, pause this video, give this problem a shot, and then when you are done, unpause the video and we will go over it. Okay, I'm going to assume that you gave this problem a shot, and I'm just going to go through it. So cofactor expansion on the 4th column is the way to go. So anyway, my sum should start positive, negative, positive, negative. So I'm going to start with negative 2 times the determinant of the, of the 1, 4 submatrix, be 6, 1, 2, 4, 0, 1, 7, 2, 2. and then plus 0 times, let me get rid of that, 0 times that cofactor, or that determinant of the minor, but it doesn't matter what that's going to be. That term is still going to be 0. And then I would do minus 1 times this determinant, 124, 612, 722, and then plus my last one, I would just have another 0 times the determinant of that submatrix. Okay, so we're not done yet. Now we have to iterate this again and figure out what the determinant of this and this matrix are going to be. And so what's that going to be? So, all right. This matrix here conveniently has a 0 in the middle, so I could expand along row 2 or column 2, and this will work out just fine. I'll expand along column 2 because the other entries are 1 and 2, and it's pretty easy to have 1 and 2 as a, it's pretty easy to multiply by 1 and 2, so that'll just make our calculation a little bit easier. So let's do it. So negative 2, I'm going to put parentheses around this entire thing so that I don't mess up. I'll have, so positive, negative, positive, negative. So I start with negative 1 times determinant of 4172 plus 0 minus 2 times the determinant of 6241, and then minus 1 times, and here it doesn't really look like there's a best thing to expand along, so I'm just going to expand along row 1. And what do I get? So start with positive 1 times the determinant of 1222, spanning along row 1, so the next entry will be minus 2 times, I'm just going to go a little faster, 6272, and then plus 4 times 6172. Hopefully I did this right. I'm not rushing too much. Okay, what do I get? So, okay, this first one, I'm just going to go ahead and distribute this negative 2 to all of my terms here. And I'll have positive 2 times 8 minus 7 plus 4 now times 6 minus 8. That'll be for the first line. And then I'll distribute my negative 1 to everything as well. And I get minus 1 times 2 minus 4 plus 2 times 12 minus 14. And then this should be, negative 4 times 12 minus 7. Okay, and hopefully I did this right. So I'll have 2 times 1, which is 2, plus 4 times negative 2, which is negative 8, plus negative 1 times negative 2, that's positive 2, plus 2 times negative 2 is negative 4, plus negative 4 times positive 5. 4 times 5 is 20, and that should be negative. Okay, what does this equal? 2. So I have 2 plus 2 minus 4, that's 0. And then I'm left with negative 8 minus 20, which is negative 28. Okay,